So as you might have noticed on my channel, there is a playlist called Projectile Motion in Sports, and it has a bunch of these videos which kind of seem unrelated, and some of them probably don't make sense, and the reason they don't make sense is because they're a part of this presentation which I made for school. So there's things like that LeBron James basketball shot. You're probably like, where the hell did I get those numbers from? Well, here it is. It's in this project. So for a bit of context, we were given the brief, I'm in fourth year, so we were given the brief of making some kind of project that shows how maths is used in sports. And I'm big into applied maths, and I've studied a little bit of it myself. So I know that the applied maths brief this year is about projectile motion in sports. So I thought it would be interesting to kind of get an idea for what the project is like, a bit of practice, I suppose, before I go into the Leaving Cert and I do the project myself. I could do the project, my TY maths project, kind of on a similar brief to the Leaving Cert Applied Maths project. And this is the outcome. So yeah, I'm just going to go through it. I'm not going to play the videos because that'll make this video way too long. You can find them in the description or in the rest of the playlist, and they'll be in order, and I'll tell you when they come at each part. So the first thing was a preface, because I was absent the day that we were told about the project, and as a result I only heard about it from my friends. So apparently it was meant to be something that shows the importance of maths in sports, but I just thought it was anything to do with maths and sports. So I tried to talk about the importance of maths in sports, but it's not the main focus of the project. I don't think the teacher really mind, so yeah, that's not really important for this, or for the average viewer anyway. So, introduction. This is very similar to like the introduction of the applied maths project brief, but basically, as you know, in many sporting events, some object is projected with an initial speed and an initial angle, and an initial angle. It could be kicked, thrown, hit with a club or bat, or it could be that the projected object is the sportsperson themselves. Like in the long jump, you're trying to jump as far as possible, you're throwing yourself, you're not throwing an object, you are the object being thrown. So to maximize your success, sports people may consider factors such as the speed and the angle of the projectile, as well as its interactions with the wind and the air. Again, that's from the applied maths brief, that's what they said. In this project, I'm going to show how I will, using mathematics, I will show how a sports person can manipulate some of these factors in order to achieve success. I'll investigate things such as the optimal angle for the maximum range of a projectile and the initial speed and angle needed for certain scenarios. For example, throwing a basketball into a net under different assumptions. So, if you are into physics or applied maths, this is probably going to be really basic, but because it's a TY maths project, I really wanted to show everything, so I showed them how I got the kinematic equations of motion that are used in applied maths, kind of in the, like the one-directional motion questions and in the projectile motion questions. I wanted to show where those equations came from, because otherwise, you know, considering it's a TY maths project, they're going to be like, where the hell did you get them from? And I think their derivations are very interesting, and I just thought it'd be cool to include them. So, how can we derive equations to describe the movement of a projectile? So, I listed out the relevant variables with which you will all probably be very familiar if you do applied maths or physics. There's the time, which is the time elapsed since the projection of the particle, the displacement s, which is the distance of an object from an initial position, the initial velocity u is the rate of change of displacement at time equals 0, and the final velocity v is the rate of change of displacement at the end of the particle's motion. And then the last variable is acceleration, which is the rate at which the particle's velocity changes. So we're going to assume that that's constant for now, but remember, drag will change that, because the drag, as you'll find later on, is proportional to the velocity, which means it's constantly changing, and it's going to change the acceleration. Since forces cause an acceleration, the acceleration is always going to be changing, because the force of drag is always changing. So, how can we relate these quantities? Well, we can solve some 3 differential equations to come up with equations, I suppose, that describe the motion of the particle. Oh, that's backwards, sorry. So that's the video. It's the first one in the playlist. I'll leave it in the description. I'll put the number 1 before it or something. Oh, that's playing it. Okay. Okay. Right, and that's that. So, gravity. Due to gravity, all objects on the Earth's surface are accelerated towards the Earth's core at a rate of 9.8 meters per second squared. And then 1 is just the reference, the website from which I found that. The symbol for acceleration due to gravity is g, right? Nothing groundbreaking. Projectile diagram. So, when using these equations, we must specify whether we're using them in either the x direction or the y direction. Both directions can be positive, which in the x direction would mean east, and in the y direction it would mean upwards, or it can be negative, which in the x direction will mean west, and in the y direction it will mean downwards. The following diagram shows the quantities for each direction, assuming there's no drag or wind. So as you can see, lots of stuff going on in the diagram. So you have the initial velocity u here, and I broke that down into the y component. If it's launched at an angle of theta to the horizontal, the y component will be u sine theta, and the x component will be u cos theta, just because of like right angle triangle is how they work. The acceleration in the x direction is 0 because there's nothing slowing it down. There's no gravity, there's no drag in this case, and there's no wind, which we haven't included yet. The max height h is just going to be here in the middle. The horizontal displacement, which is called the range, which I'm using or to show, and then the time is going to be the same for both directions. So however long it takes to do 5 seconds in the x direction, is also going to be y direction after 5 seconds. You can find it out. So it's going to be the same. That's a shared variable between both. And that's very important later on when we're kind of solving things, because we can substitute in the time in equations. So if a projectile is fired with an initial velocity u at an angle theta from the horizontal, these are the values we have. So for the displacement s in the x direction, we have or, which is the range. The initial velocity u will be u cos theta, the acceleration will be 0, and t will be t, and v depends on where in the motion we're looking at. So if you're looking at when it's at its highest point, which you can't really for the x direction, that's when v is equal to 0. But in this case, v is never going to change because the acceleration is 0. V is equal to u. Because v is equal to u plus at, if a is 0, v is equal to u. So in the y direction, you have the displacement is h, the height. The initial velocity is u sine theta. The acceleration is negative g, which is negative 9.8 meters per second squared. Negative because it's going downwards. And t is just the time. It's the same time as the x direction. And again, v depends on where in the motion we're looking at. So if you want to find when it's at the maximum height, you could find when the v is equal to 0, that's when it's going to be at its maximum height, because that's just before it starts falling back down again. But how is this relevant to sports? So I wanted to show how can we apply this to sports. So to apply the theory of projectile motion to sports, we will consider a general application and a specific application. So the first thing I did is I came up with a general application. So this is for deriving an equation for the maximum range. So in the long jump, contestants must jump as far as possible. And in golf, the ball must ideally be hit as far as possible to get as close as possible to the hole in the fewest numbers of hits. How can we optimize the initial conditions of a particle's projection to maximize the distance or range? And I showed that in this video, which will be the second one in the description and should be the second one in the playlist. I'm not going to play it now. Oh my god. Okay, and that shows you that the angle you should throw it at is 45 degrees, and just make the initial speed as fast as possible. You could probably guess that. Not very groundbreaking. The next thing I looked at was the specific scenario, which is this basketball shot by LeBron James. So I said, let's apply the theory of projectile motion to a real-life problem. Observe the following clip of an almost full-court basketball shot by LeBron James. Now, I actually am going to show this because this isn't in the playlist, so I'm going to play it right now. So you can see he just throws the ball. Oops. He throws the ball from one side of the court all the way to the other and gets it in. So that's what I decided to base it off. Oh, no, don't play again, please. Okay, so the horizontal displacement slash range. So using this diagram, which is source number 2, we can figure out the horizontal displacement of LeBron James from the net. So this is all in like inches and stuff, I think. But basically, you can see how far like the net is from the side of the court. You can see how far it is from this line. You can see everything, the length of the court, the width of the court. I'm not really into basketball. They might have proper names. I'm sorry if they do. But yeah. So after some calculations, we can conclude that his displacement from the hoop is approximately 27.2 meters. So as you can see in this previous one, so there's 4 inches between the side of the court and the hoop. And then I guess I just converted that to meters, or maybe it's not 4 inches, maybe it's 4 feet. It is 4 feet actually. So that's about 1.2 meters, and then that's the hoop, and I just took the center of the hoop, the radius of the hoop I found, and I just said in the very middle is 0.2 meters, and I did some calculations, a bit of geometry, came up with how far it is in the upwards and how far it is across, and then I used Pythagoras' theorem to find the direct distance from him to the thing. So honestly, it's hard to explain. This is really messy, but just take my word for it. In terms of the vertical displacement, LeBron James is about 2.06 meters tall, according to most websites, and I showed the source from which I got that. He appears to let go of the ball at approximately head height, so we're going to say that the ball starts its journey at 2.06 meters above the ground. and an NBA basketball hoop is about 3 meters above the ground. So therefore, the vertical displacement of the ball is 0.94 meters. I just got the difference of those two. The time taken, so I downloaded the clip and put it into a video editor to see the exact time that the shot took, and the time taken was approximately 2.57 seconds, although it was hard to see due to the bad camera quality and the distance of the ball from the camera, but it's around 2.57 seconds. Now that we have all of the easily measurable information, let's see if we can calculate the missing information. So here are the variables we had: the horizontal displacement 27.2, initial velocity u cos theta, a is 0, t is 2.57. In the y direction, s is 0.94, u is u sine theta, the acceleration is negative g, and the time taken is 2.57, which is the same. Considering we have two missing variables and two equations, that means we can we can calculate the initial velocity and the angle of projection, because if we have two equations, two unknowns, we can solve that using a system of equations, which I do in this video, which now probably explains where I got all those values from. So, yeah. So the angle of projection, this is something I actually forgot to include in the video, which is my bad. So I said, note, the angle of projection can have two values. These will be 45 plus or minus c, where c is a constant. So since my answer of 50.66 degrees is 45 plus 5.66, that means 45 minus 5.66 also works, which you can use the graphs on slide 43 to verify. Therefore, the possible angles of projection are 50.66 or 39.34. And I'll put those graphs in the description if you want to mess around with it yourself. They'll all be there, so you can verify that this is true, or just play around with it yourself, you know. So, do these results make sense? So, the results, in terms of the angle. Looking at the video, it's safe to assume that the ball is thrown at an angle somewhere around 51 degrees to the horizontal. And now, in terms of the velocity, according to an ESPN Sports Science study, which is source 4, LeBron James can throw a basketball at about 40 miles per hour, which is about 18 meters per second. And that's only 1 meter per second faster than the answer that I got, which, when rounded, is 17 meters per second. So I thought it was a really good approximation for those reasons. But now what happens if we take drag into account? And this is when it gets really complicated. So, what is drag? Drag is a force that slows the movement of an object through a liquid or gas. I could just say through a fluid, but yeah. Anyways, as a moving object pushes the liquid or gas out of the way, the fluid pushes back on the object, reducing its speed. Source 5. Examples of drag. You feel a drag force when you try to move your hand in water. The faster you move your hand, the harder it is to move, which you've probably noticed before. The force of drag always opposes the movement of your hand and depends on how quickly you move your hand. Drag is a big deal for professional swimmers, because if they can reduce drag, they can move faster because they're not being slowed down as much. But how can we calculate it? So, when a particle is moving at slow speeds, the drag force is proportional to the velocity of the particle. But at higher speeds, it's proportional to the square of velocity. And then I showed this little cool graph, which I found on the engineering toolbox, which shows how the drag force in newtons increases as the velocity in kilometers per hour increases. So I thought that was pretty cool. Then I also showed the drag equation. So although there is a drag equation, it's very difficult to use because it results in coupled equations of motion that make solving very difficult. Now, I didn't put this in, but it's important to say that's only if it's in two dimensions, because the Vy and the Vx are going to be in both equations, and it's just really hard to solve them because you're not going to be able to integrate, sorry. No, it is differentiate. Wait. Okay, whatever. It doesn't really matter. You're not going to be able to integrate / differentiate because you have two of these variables in each equation. It's just really messy to work with. The only way to really do it, as I say here, is they can only be solved numerically using computer programs. So you could get a computer to calculate the velocity every 0.01 seconds and then graph that. Or find the value there, and that works perfectly fine. It's just I wanted to do it the more mathematical way, and I'm also not very good at programming, so yeah. This means we can't come up with a general formula using variables, or at least we can't easily, and in my case I couldn't find anything that would let us do that at all, coming up with a general formula using variables with a quadratic drag. So therefore, I opted for linear drag. So despite being less accurate for higher speeds, such as for a basketball or a golf ball, I will use a linear drag model as it's much easier to solve analytically. This means that drag will be proportional to the velocity. So that means we can say that drag equals minus kv, where v is velocity and k is a constant. And in order to determine the constant of proportionality for the drag, experiments are usually done. So now I talked about how are we going to go about getting drag. So the equations of motion with linear drag. According to Newton's second law, acceleration depends on the force applied to and the mass of an object, which is source 12. Since the drag force is a function of velocity, our original equations of motion will no longer work, because we assumed that the acceleration was constant while we were deriving them. So, this is how I came up with my new equations of motion. So, with linear drag, this is video 1 of 4. Again, they'll all be in the description and in the playlist. This is the second video, 2 of 4. And then there's a little break here, because 3 of 4 is a little complicated. So, yeah, I'm not sure if this is actually the best way to calculate k, but I'll talk about that afterwards. So, I went on to say that terminal velocity is the fastest speed attainable by an object as it falls through a fluid. It occurs when the force of gravity is cancelled out by the force of drag, meaning the particle can no longer speed up, and that's a formula for the terminal velocity, which is derived from the drag equation, the quadratic drag equation, which is very important, because I used terminal velocity from a quadratic drag equation, and I used that in a linear drag equation, so that probably messed things up and made them less accurate, but honestly, my brain is fried from all this. I wasn't bothered to look into it anymore. It was really straining. So in terms of the terminal velocity of a golf ball, here are the values I got. So the mass of the golf ball, the falling object, 0.046 kilograms, 46 grams. G is the acceleration due to gravity. We said 9.8 meters per second squared. Rho is the density of the fluid through which the object is falling, which is 1.293 kilograms per meter cubed. That's for air, the density of air. A is the cross-sectional of area, which for a golf ball is just going to be a circle, which is pi r squared. And I found the radius to be 0.2134 meters. And then when you calculate the cross-sectional area, you get 0.000444 meters squared as the cross-sectional area. And then I talked a little bit about the drag coefficient. So the drag coefficient is a function of the Reynolds number, which depends on the speed of the particle we're looking at and the temperature of the air. Wow, it gets even more complicated. So, then I went straight into the video. There are errors. So at 229, I think the characteristic length in the Reynolds number equation can be taken to be the diameter of the ball, which is 0.04 meters. And at 506, I accidentally set or E equals 8 times 10 to the power of 3 instead of 8 times 10 to the power of 4, which ends up with me still getting the same answer of the coefficient of drag being 0.25, but I just wanted to point that out. And here's how I calculated the coefficient of the constant proportionality. And before I move on, I just want to say that for that constant of proportionality, I think what you can do instead, which would be a lot easier, is instead of doing it with the terminal velocity like I did, something that I saw a few other people do is, see, this is the equation, the drag equation. So instead of, if we say FD equals, and then U squared, that's going to be the velocity. If we let the rest of this stuff equal K, so a half rho coefficient of drag and the cross-sectional area, if that's equal to K, you can just use that as your value of K. And I think that actually might be more accurate than the way I did it. I don't know why, but I'm pretty sure it is. So if you know anything about it, please let me know. I'm not bothered to research it anymore, because it's very tiring. But yeah, I don't know. If you know about it, if anyone knows about it, please comment. I'd be very interested to know why it's more accurate, or why it isn't more accurate and I'm wrong. I don't know. Anyways, so I derived that in this video, and then I analyzed the equations in this video, because I think it's important, instead of just deriving equations, that we can look at these equations and verify they're true and understand what's happening in the equations, instead of just being like, oh, here's a bunch of fancy numbers that coincidentally give me the right answer, you know? So the optimal angles I found for a golf ball was 42 degrees. For a basketball with my value for terminal velocity was 36.2 degrees. And for a basketball with the internet's value for terminal velocity, it's 40 degrees. So you can see the optimal angle is actually a bit lower. And this makes sense. So because if we're trying to get the maximum range, and since the drag is going to be slowing it down in the horizontal direction, and therefore reducing the range, in order to get the maximum range, it's logically, you would think, oh, I'm going to have to fire it more horizontally to make up for that loss due to the drag. So I'm pretty sure that's why they're lower than 45, like without drag, but again, could be wrong, that's just my theory. Here are the graphs, so you can play around with the graphs yourself using these links, and that just links them all. Make sure that you are in degrees mode instead of radian mode, and graphs use the golf ball values by default, which is the golf ball values that I calculated in the previous videos. Potential errors, because some of them like some of the things didn't seem realistic, especially for the basketball. It didn't really seem correct. These linear drag equations may be incorrect because the terminal velocity formula I used assumed quadratic drag. The drag coefficient is a constant, but I assumed it to be one, or I just made a small mistake somewhere. Happens to the best of us. Then I wanted to compare my answers to the simulation that I found online. So this simulation I found, it calculates, like, you put in the initial conditions of a golf ball and it predicts how far it's going to go. So, for example, if the initial velocity is 40 meters per second and the angle is 30 degrees to the horizontal, how far will the golf ball travel? So when I put this into this simulation that I found that the range will be 106 meters, the max height will be 26.4 meters, and the time taken will be 5.4 seconds, as you can see here. So for my equations with the drag, the range I got was 86.7 meters, which is 19.3 off from the simulation's answer of 106. The max height was 15.85, which is 10 meters off, almost 10 and a half. Whereas you can see there it's 26. For the time taken, 3.61 seconds was 1.79 seconds off what I got in the program or in the simulation. And the answers from my equation without drag, so the range was way off. It went way farther than it should have. 35 meters, that's a big difference. Interestingly though, the max height was only 26 meters off, which is actually better than my equations with drag. And the time taken was only 1.3 seconds off instead of 1.7 with the drag equation. So interestingly, the no drag equation is actually more accurate for these certain things. And I propose a theory for this. The no drag situation may have been more accurate for the maximum height than the time taken because, again, my drag model is linear drag instead of quadratic drag. Quadratic drag is more accurate for fast objects moving through the air. So that could just be a problem with the thing I did that causes not quadratic drag. It's not as accurate as the simulation is, or it's something that I'd really like to look into, but again, I'm just not bothered to. I didn't take the spin of the ball into account, which I'm guessing would make it go higher and thus giving it more time in the air but a shorter range. Hence why the no drag scenario for its range is so far off. Because when you think about it, if the ball is spinning, it's going to like spin to go upwards, and that's going to slow it down, so it doesn't go as far, but because it's so high up, it's going to spend more time in the air. Or maybe that's wrong, I don't know. Again, if you know anything about this, please comment down below, I'd love to know. But what about the LeBron James basketball shot with linear drag? So then using the values I showed earlier, I calculated it in this video, which again, it's going to be in the description, it's going to be in the playlist. And the results I got with no drag, I calculated these earlier. So with linear drag, I found the initial velocity to be a lot faster, and the angular projection to be slightly higher, or slightly, it's a fair bit lower than the one I calculated, because I only added in this 39.34 a bit later. So recall that earlier I found that the LeBron James can throw a basketball at 18 meters per second. This makes the no drag scenario seem more likely. I genuinely don't know why the answers for the initial velocity are so different. Like, it makes sense that you need to throw it harder to make it go faster to compensate for the drag, but like, I don't see why it's that big of a difference, and I'd love to know why. So if anyone has any ideas, please let me know. Recall as well, however, that the optimal angle to throw a basketball for the maximum distance, according to my fourth video about linear drag, is about 40 degrees, which is more accurate for the linear drag scenario, but not by much. Although, bear in mind, I think I am going to have two values for the linear drag. I just didn't find them. I don't know why. I think I was just really tired. And if we only take the first value I got for the angle in the no drag scenario, the linear drag is way more accurate. But once I calculate the other possible angle, which I know for a fact he didn't throw at, but whatever. Well, no, I don't know for a fact. He could have thrown it at 40 degrees. Anyway, the point is, like, it's about 40 degrees for the optimal angle for maximum distance, which is more accurate for the linear drag, but not by much. I'd say it's such a small, tiny bit more accurate that it's probably just like a lucky approximation that happened somewhere that made this slightly better. So I think it's interesting that the no drag scenario is actually kind of more accurate. I'd love to know why, because I'm kind of annoyed after all this work that linear drag ended up being wrong. Well, not wrong, but like more far off, or what seems to be more far off. But oh well. The other value of k might have been more accurate, though I doubt it. So remember earlier I said I calculated two different values for k, because I found a terminal velocity online and calculated my own terminal velocity, and I don't know which one was actually correct. But I didn't have time to check. I didn't bother checking because I doubt it, but you can if you want. just for a bit of fun, I decided to say, what if we do it in the moon? So if the shot were taken on the moon, where the acceleration due to gravity is 1.6 meters per second squared, and there's no air and therefore no drag, he would have thrown it at a speed of around 11 meters per second at an angle of about 13.06 degrees or 79.64 degrees. But why? So, the ball doesn't need to be thrown as high because the ball falls more slowly due to the weaker gravity, which is why 13.06 degrees will work. Yeah. Like, it's a lot lower than what we got previously. As well as that, the initial velocity doesn't need to be as high, since more of it can go into the x direction rather than the y direction due to the reduced gravity. So, as well as that, it's going to spend more time in the air. So, like, if we did 76 degrees, it's going to be so long in the air because the acceleration's so slow, bringing it downwards, that, like, it's going to be traveling in the x direction for so long that it just doesn't need to be thrown as quickly, because it's not going to fall as quickly, so there's no rush to get that distance in time, you know? Anyway, and this is kind of the end where I try to tie it back into how is this important in sports. So the designers of sports shoes and sports equipment, like golf balls or swimming suits, can use the study of drag to design their products in a way that reduces drag as much as possible and thus maximizing performance. Sports people can use things such as the optimal angle that I calculated to maximize how far they can throw a projectile, like a javelin, or yourself, like the long jump. And then I just did a quick conclusion. It's really cool that we can mathematically model how projectiles in a sporting scenarios work, regardless of how accurate it is. Like, even though these mightn't have been accurate, they're still really interesting how we can, like, come up with those and look at the graphs and see how far they go. I think it's really cool. While both models could tell us a lot about certain sporting events, neither are perfect. If I were to take quadratic drag and the Magnus effect into account, the Magnus effect is just like kind of the spin on the ball, I might be able to model the projectiles in sporting settings more accurately, as well as that wind as well. Wind isn't too hard to incorporate, I don't think, although when I was kind of brainstorming, there are a few ways you could go about including wind, and I didn't really put much thought into it, but I guess one of the ways would be really complicated. Again, might do that another time. I'm just not bothered at the moment. But that require many more hours of research and frustration, so I'll leave it for now. I know that I also probably did way too much for this project anyway, but I had lots of fun with it, and I got carried away. Thank you for reading, because a lot of my friends, they just said, like, oh yes, so we can use maths to, like, calculate the breathing rate of sports people, and then they can change their diet. So I think the difference was some of them did talk about, like, drag and, like, how things move through the air, but most of them just said, oh, you can use maths to calculate drag. Whereas I was like, you can use maths to calculate drag, and here's how you can do it. So I think that's kind of why I said it's probably too complicated, because I don't think we actually had to calculate the things. I think we just had to say why it's important. And then we just have references, so they're numbered. You could see them throughout the slideshow, and that is it. So, yeah, I hope that makes sense. I hope that clears up, like, why the LeBron James videos seem so random, and I hope you enjoyed it as well. Again, if you know anything about this that you'd like to, if I said something wrong, or if you know anything that I could add, or basically anything, like, about mistakes or interesting things, please comment them down below. I'd love to hear, but that's it. Thank you for watching, and, yeah, goodbye.